Thank you for coming. I think we're a bit behind schedule, so I'll try to rush through 98 slides in, we'll see how long. I shall reset my timer here, and then we can go. So this is a bit of an arrogant talk title, because I'm telling you your architecture isn't ready, which is probably not true, because you're all very smart and perfectly capable of building great systems. The cloud is the future, clearly. Everybody has heard of that. And the question is, are your architectures ready? My name's David. I work for a company called Heroku with sparkles. And you can email me if you have questions. We also have a booth. You can also, for the next 40 minutes, while I'm unable to defend myself, praise or shame me on Twitter. So Heroku, we're a platform as a service. And we're now pushing, I think, upwards of 8 billion requests a day. We have a lot of, millions of apps, lots of add-on partners. So over the years, we've learned a lot of things about how should systems be structured. We're now in our third and fourth generation of software stacks. We call it Cedar. And the stacks before that had certain limitations, right? Not severe, but every iteration we make, when we make changes to our systems, we built them in such a way that they are more ready for the future and for the demands of things that need to scale horizontally, usually. So I want to talk first about how the cloud is the future. And it's actually, I'm not going to talk much about computers. There was a time, imagine tens of thousands of years ago, and there was people who lived on both sides of a canyon. The canyon was deep. Some brave men and women sometimes climbed down and up the other side, and then they high-fived the other people, right, on the other side. But not a mutual language. It's really hard to learn the other person's language if you're soaked and cold or died, because this is when dinosaurs were still alive, right, and humans at the same time, because we all know that's true. So the dinosaurs would eat you because in the river and stuff, and it was just not a comfortable situation. They wanted to get across the canyon safely, but it was too long, unfeasibly long to just walk around or something, because you end up with an ocean on either side. This is a different planet, maybe, it doesn't matter. So one day a visionary said, hey, let's just toss some boulders down, right? So, and then the people on the other side saw this, and they also tossed boulders down. And eventually, they filled up the whole void with stones and rocks and boulders. And they were able to walk across, and they were able to trade, and they got married, and they exchanged ideas and languages and stuff like this. But while that was happening, the level of the river was rising because they built a dam. And eventually, it flooded everything, and it was a huge disaster. So they said, well, we kind of need to find a way around this. So another couple of people then climbed down again on the dry side of this dam and just removed some rocks, right? So the whole thing just collapsed a little bit, and yeah, they had the same problem again. But eventually, they figured out how to make an opening that was stable in the form of an arc. And that was the first very crude bridge. That's not the same canyon, okay? It's the different canyon, just in case you were confused. And this is more suitable for a little creek and not for an actual river. But you get the idea. So they had invented the first bridge, and eventually they got better at figuring out what the exact shape of the arc needs to be, right, and how to arrange the stones. So they built things like this. This is not for a river, I don't think. It's I presume, standardized Roman horse with a standardized Roman horseback rider would fit neatly underneath without hitting his helmet. But the opening is already larger, right? And then somebody said, well, that's a stupid amount of stones. Can we just not use fewer stones to make a bridge that's stable? And that's called engineering. Somebody figured it out, probably without the help of a calculator back in those days, right? So this is probably the minimal bridge you can build with stone. Anything with fewer stones is going to collapse, because stones have their own very high specific weight. The Romans then got really good at scaling that. They made standardized bridge parts for the aqueducts, right? So this is a horizontally scaled bridge, right? You just reuse parts. And then iron was invented, and iron is cool because it's even lighter than stones, right? So you can build, maybe not bigger bridges, but at least you can build bridges that use less material, that are probably easier to construct than a stone bridge. But an iron bridge has a certain maximum size, right? Because the tensile strength of iron is not the same as that of steel. So when people invented steel, they said, hey, cool, we can build bigger bridges. And then eventually people figured out, well, we can build suspension bridges, right? So the span of whatever void the people want to cross gets larger. The material required for it gets smaller and smaller and smaller. At the same time, we can at least carry the same, but probably a higher amount of people across in vehicles, on horses, on foot, on bicycles, right? So the bridge is getting smaller and smaller and smaller. Maybe one day it's going to disappear entirely. There's a river, and you can float across without a bridge. That's not entirely unrealistic, right? I mean, the moon isn't tethered to the Earth with a cable. It's gravitation. So once we master gravitation, we don't even need bridges anymore. And then we transport all the people with none of the material necessary that we used in the olden days. So this is a story that was often relayed by a man named Buckminster Fuller. Who has heard of him? Okay, it's a computer conference, not an architecture conference. So it doesn't surprise me. I hadn't heard of him until a couple of years ago either. So he was a clever man. He had lots of good stories to tell. He experimented with things. He wasn't so much an architect. He was a bit of an architect, a bit of a crazy engineer, scientist guy, who always tried to reinvent things, make them smaller, make them composable, repurpose things into smaller things, abstract problems away. He was very much like a computer person, except that he dealt with things in the physical world. So he had this mantra, or this assumption that we're able to do more and more with less and less. And then one day, we can do everything with nothing. That concept is called ephemeralization. Ephemeralization. The idea is that in the cloud with computers, but also in the real world, you can make complexity disappear downwards, right? If you think about how vehicles are constructed nowadays, car parts come from suppliers, and the engineers who build a BMW or a Peugeot, of course, or something else, they have no idea how that little, ultrasound sensor works. They don't have to care. They just use a toolbox with parts. So do we in computers. We use, in software development, we use Symfony as a framework, which in turn maybe builds upon other libraries and stuff like this, right? It means composability of parts who can disappear or be replaced at any time, right? Because they're abstracted and they have standardized interfaces, maybe. The underlying noun or adjective is an ephemeral. And if something is ephemeral, it doesn't last very long. It's transient, right? Not persistent. And so he says we can do everything with nothing. But really nothing? That's the question, right? Can we achieve that? So if you think this place is a theater, theaters were for centuries the predominant method of entertainment for people, right? You went to the theater. You watched a play. The problem with that is that it doesn't scale very nicely, because if more people want to watch the play, they need to go to the same theater, right? You can't, unless you replicate the theater troupe, in which case there's slight variance and stuff, but it's difficult to scale up horizontally a theater. So then somebody invented film. And the cool thing about film is that you can go to the cinema, you can make copies of the film, so 500 cinemas can show the same film. But film cinemas used to be really crappy as well, because they showed one film per week. It was some stupid propaganda. They needed an actual orchestra to play the music, and they didn't have your favorite beer, and you missed the most important bit of the film, right? Even nowadays, you drank too much beer. You need to go to the bathroom, and you miss the scene where the Arnold kills the bad guy, right? We'll be back. So you come back, you're angry, wasted money, and the thing is that you go to the cinema and they show the films they want, which is a little bit annoying. But compared to a theater, it's actually like a big step forward, right? And then there was a great invention, video. That doesn't store film pictures anymore. It stores a signal for a picture on a screen. And all of a sudden, you go rent or buy a video cassette. Who remembers these? Yeah, okay, good. I'm not that old. So and you can record something on TV that's amazing. You can go to the restaurant because you prefer that, but the TV show you can still record, right, and watch later. So all of a sudden, you don't go to the film comes to you. It's still a horrible experience because somebody said, I missed that scene, so you try to rewind, and then you rewind too far, and then somebody says, I've already seen that, and it's just blurry, and it's bad technology, and Betamax would have been better, but that's life. So there was a big step forward. All of a sudden, you're in your living room, and your favorite beer is in the fridge, and you can hit pause if you need to go to the bathroom, or the doorbell rings. And then DVD, obviously, is a really big step forward because it's much nicer quality. You can jump to chapters and stuff like this. But arguably, in my opinion, a bigger step forward was the Blu-ray, because all of a sudden, for the Blu-ray, you don't even need a separate playback device anymore, because you already have the PlayStation 3 or 4 at home because you love Gran Turismo, and it also plays films, right? So in order to play that video, it's just a thing that already exists. And now, most people you might have a TV or a computer, the concept is the same. You somehow, even if in the future there's going to be a picture that's beamed into your retina, you then need to place a hat on your head or something like this, right? So there's always a playback device, some sort of screen in one form or another. And that screen, the TV, now has smart functionalities, at least that's what the manufacturers claim. And it contains a Netflix client, right? So you went from a theater over a movie theater where you need to go to the place, right? And you need a massive building to show one film per week to all the films in the world in no device at home because it's already built into the screen, right? No apparent device. But the thing is that Netflix doesn't run on nothing. It runs in the cloud. It's just that all the visible complexity to you, the video cassettes in this room, was pushed further down the stack, right? They run in a data center and in another data center. This is just the same one. It's just mirrored. But you get the idea, right? This is a different availability zone on Amazon. And they run all this complexity, but they, in turn, don't have to deal with networking and all these things. To a certain extent, Netflix does because they are big, but still, if they have network congestion or something, they have a couple of technical account managers at AWS. They call them in the middle of the night and say, like, this show we're releasing, I don't know, House of Cards. It's buffering too often for people, fix it. So they have pushed their infrastructure concerns down. And it runs on composable parts, not on a supercomputer. And even supercomputers these days are not specialized machines anymore. Even Cray, the prototypical supercomputer manufacturer, now builds systems, this is IBM, but you get the idea, out of its racks of x86 hardware, horizontally scaled nodes based on commodity systems. Right? So in order to facilitate that, something had to change. Because the software that runs on these supercomputers is not the same that ran on the old supercomputers. And I'll get to that in a moment. But in general, there's an evolution in infrastructure in everything we do, from bridges to computer networks. And even the cloud has evolved over time, right? Because we went from software as a service, that's the first, like hotmail.com or something like Salesforce or something, where you have a software product that you don't need to install on servers anymore. Infrastructure is then Amazon, and then platforms as a service such as Heroku, Platform.sh, etc. They even take away the complexity of managing networks and Linux versions, right? So ephemeralization is about making components minimally visible, or invisible ideally, right? And these components should be simple. You build on strong foundations if you have simple components and parts. If just a lot of simple things build on top of one another, it's much, much more reliable. and durable than a system where you have complex parts building on top of another, because there's a lot more things to go wrong in complexity, as we all know. So that makes it resilient. And Buckminster Fuller called this the kit of parts, right? So that's what we do nowadays, like to a great extent in the cloud. I mean, on infrastructure as a service, you still see the components, right? They're virtualized, but you still deal with server instance stuff. That's why Amazon is adding a lot of features that go more in the PaaS direction, where you don't have to worry about backups or how your code is shipped out, right? Or the classic platform as a service promise that we or other competitors make, where we say, you just push your code and we worry about everything else, which is mostly true, not always. You have a little bit of responsibility. But this is where you end up with, in the cloud, you build things out of like little parts, right? You say, make me an app, give me a Postgres, give me a Mongo, give me a Redis, give me a worker queue, give me a Blackfire, right? And something for my private Composer repo, and push the code. And then it works. And so you don't have to worry about a lot of stuff, right? It's almost like magic, except that it's not that there's magic involved, it's just you can't see the parts anymore. So you make an app, and if you build it for this promise, then they are very portable and reusable. How to do that is going to be chapter 2 in this presentation. But step by step, the infrastructure underneath also gets simpler, right? And more componentized, ideally more portable. So Azure, for a while, I don't think they ever deployed it, but they pitched to customers that they could have their private Azure cloud, a shipping container that Microsoft delivers on a truck and puts into your company's backyard. It cost a couple $1 million, so nobody bought it. But IBM does the same thing. This is the true decentralized cloud. This probably runs Docker containers inside, but you know, it's a container and there's a little data center inside. And because your software doesn't care what data center it runs on, it just sees a bunch of boxes. It probably doesn't even see a bunch of boxes. You just push code and say, this is how much power I need, right? It's all possible. But you can't build an application like you built it 15 years ago and expect it to run on 10 of these things on different parts of the world. Because all of a sudden, certain characteristics of the underlying system change. And that's volume 2. Your architecture isn't ready, I think. I fear. I hope it is. So systems complexities get pushed further down the stack, right? We just build on things, on things, on things. Then stuff like Docker comes around and says, oh, everything's easy, don't worry about it. Just do, here's the command line thing you can't remember, and then it's going to fail randomly. It looks like this. But you know, Docker's not replacing the cloud or Amazon or Heroku. It's orthogonal to that. It's a way of packaging things up, and in my opinion, it's maybe not the perfect solution for many super dynamic languages. But what it makes easy is having little individual components. So all of a sudden, it becomes easy for system administrators to say, well, the MySQL thing really is a different container from the application server, right? The system architects who say, well, we need low latency, blah, 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 still demand that it's locally, but it's not actually anymore. All of a sudden, you have, ideally, the ability to decompose things. But that means your code needs to grow up, because all of a sudden, responsibilities bubble up the stack. As you push certain complexities that you don't want to deal with in your code further down, that also means upwards comes problems that you now need to deal with on a code level, which I think actually makes our applications much, much better, right? We are hopefully done very soon with 700 lines Puppet or Chef recipes to deploy an application, because that's just ridiculous and shouldn't be necessary. In many cases, these are artifacts of how badly an application is designed and not how what's necessary to get it running. But modern infrastructure, right? Think of it as an ephemeral kit of parts, like the bridges that got smaller and smaller. And your code needs to account for that, right? So one of our competitors for a while had a directory on their web servers mounted via NFS. So you could have 10 instances running, but if you tried to run 100 instances, it just wouldn't work, because that would be a bottleneck, right? You can't mount a system directory or any data directory between nodes and expect that to infinitely scale horizontally. You, in your code, need to make provisions for the fact that you're storing data on some external storage that scales independently, right? Don't just, because this is a typical example of system administrators magically saving the day. They, on a Saturday night, see that the application is slowing down, and they change something about the NFS configuration so the site remains online, right, on Cyber Monday. And the developers, they just wrote code that does an fopen on the local disk, because the code doesn't know that it's actually not local data, right? That works to a point, and then everything collapses, and then everything's on fire, and everyone's freaking out. Persistent file systems between deploys, like all of these things are complicated, right? If you just want to push something up, in particular with Docker, you can't do it anymore. In Docker, you can externally mount a data container, but if you have a container with your application and it writes stuff to disk, if you replace it with a newer version of the container, the data's gone, right? And if you think about it, why would you even go through the trouble of having a /data directory that then there is a script somewhere that the sysadmin wrote that you don't even, as a programmer, don't even know about, that backs up the data but not the code, because the code can always be redeployed? That's complicated. But it's a point where we arrived at because we evolved our infrastructures from what we did 15 years ago, where we had an FTP client open and we just dragged and dropped .php files over, right? And this is not a PHP-specific problem. This is, all languages do it weirdly like this. Database credentials change suddenly, maybe in the middle of the night, because something bad happens. You need to fail over to the hot standby. All of a sudden, you need to connect to a different database server, right? At Heroku, we regularly do this. Like in the middle of the night, you'll get an email, hey, in 10 minutes, we're going to be doing maintenance in a database, which means we move it to a different instance, we restart your app, and it gets a new environment variable with a database connection. If you then have your database credentials hard-coded in your code, your app's going to go down, right? For Docker, you need this, because Docker is, your code is in a container, and what database to connect to, you tell it through an environment variable externally. So you have the code separate from the configuration. That's the future. There's no sysadmins saving the day, right, or night, like we just talked about. There's no installed existing web server with a data directory you dump your stuff in and you can install an extension on it. It's all part of whatever container or software thing you run, right? It's one bit self-contained. A lot of these principles are encapsulated in a document or a manifesto called the 12-Factor App. Who's heard of it? Quite a few people. Everybody else should read up on it. It's a manifesto and a methodology, and basically collected experiences over time of running large-scale systems. And, you know, Platform.sh, Heroku, Azure, they all adhere to this. Docker is very compatible with this, because the principles it lays out make it very easy to maintain systems, to recover from crashes, to back things up, to figure out across your 100 web server instances, where is the process that crashes all the time. So you want scalability, you want stuff to be maintainable and maximally portable. You can read up on it at 12factor.net. That's the site, and it shows every single principle. So use that as a reference when you build things. I'm going to swiftly or not, depending on the factor, walk through them just now, just to explain a few of the thoughts behind these rules, right? Why do they exist? So factors number 1 to 4 is, the first is you have one code base. And from this code base, you perform deploys to different environments. I hope I don't have to explain that. Clearly, we don't want, we don't have subdirectories in production for a testing environment or something, and we use SFTP to put stuff up. I hope we're all now deploying something Git-based or with a continuous integration service. And then we probably have different environments, right? Prod, dev, stage, with different configs, which is fine. Dependencies are managed by Composer in our case, or NPM if it's Node.js, Bundler if it's Ruby. And an application declares these dependencies. So you can ship the code without its dependencies. They get installed properly, makes it portable, makes it lightweight, easy to deploy because it's not 700 megabytes of PHP, it's 50. And the configuration, maybe even the configuration that tells the system you're currently in production or staging or development mode, comes from the environment. So you have maybe a database URL that you read from $_env, right? A debug mode, flag on or off, log levels. Because then you have the code running, a Docker container that runs, you change the configuration on it to say log level is now debug, and all of a sudden it spits out more stuff. You need to restart it, but you get the idea. And the fourth is that backing services are a thing and you don't know where it lives, right? Your database could be running on that IBM shipping container on the corner of the road. It could be running on the local machine because it's your development thing. But the means through which you connect to it is always the same. You read some config and you do it. So dependencies should be clear. In case of Node, a package.json looks like this. In case of Composer, a composer.json looks like that. And you can actually, there's nothing stopping you. At least we do that. Like when we see, hey, you want that PHP version and that extension and stuff like this, we install that. If that says MySQL, you never get PHP 7 because PHP 7 doesn't have MySQL, right? The extension. And then userland code, obviously, that then gets installed on deploy. And the dependencies shouldn't be in your Git repository, please, because that makes things a lot easier. Configuration in the environment, right? Because the idea is that you have the code and it can do vastly different things depending on how you configure it. You can switch some sort of sandbox mode on for the payment gateway, or when the environment is set to prod, it uses the actual production payment gateway, otherwise it uses a dummy thing. Email gateways are set up differently, right? So you always use the same SMTP library to connect to an external service, but in staging, it's configured with a catch-all address, so all the email goes to your inbox. In production, it actually goes out to customers. Not everybody does this. You have probably in your lifetime all gotten marketing or notification emails from a service you signed up to, but it came from the staging environment, because sometimes developers cut corners and they hard-code things. So you can just read this stuff and do a config set of some kind. Or in the case of Docker, you have you pass it in the Docker run command, or you have an end file where these. Does this have a laser? Middle button. Oh wow, cool. So email host and stuff like this, right? You can configure these in a Docker for a Docker container and it runs, but you don't actually need to use several variables. So you can just parse the URL and set one URL. And that's really easy. And then whether you connect to Redis or a database or an SMTP server, you can always phrase it through one configuration variable that you just parse at startup of the application. Now, this is obviously easier to do for a Java app or a Ruby app, which starts some code, can read this stuff, configure the database, and then it starts an internal web server to bind to a port, right? In the case of PHP, it means the first request hits, you have never read database URL or SMTP gateway URL, so now you need to maybe cache that somewhere. In Symfony's case, it actually means that when you deploy, it already creates a cache. That cache is then part of your running application. So when the database URL env changes, your code never sees it. There have been some attempts to fix that, but basically, before your application starts, you should clear the cache. And that works around most issues. But yeah, the golden rule is don't hard code your config, right? Because the config might change. Build, release, run is just the sequence of how things work when you deploy code to a 12-factor compatible application. Processes mean you can scale things independently from one another. Most of these processes bind to ports for web, for instance. It's not that relevant. And you scale out using the same processes from number 6 that you deployed in number 5. So to build, release, and run something, you have a build step that vendors in the composer dependencies. Even PHP itself, maybe the web server needs to run everything that's required inside the container. So this could be a Docker build, or this could be a git push to whatever service you're using, right? And then it releases a new release that you can maybe even roll back to and stuff from the code you pushed and the configuration. and the runtime then runs this. So that's what it looks like. And the build step, right, produces some code. That could be a Docker container, a built Docker container. And together with some configuration, you run it. So Docker container or a Heroku builds that together with its config makes a release. So you create an application, you push it, it detects everything, right? And that's how it builds something. And then this becomes the built application. And then through a config set, you say, this is the database URL, I want that code to use at runtime. And when you change the database URL, you don't have to rebuild the code. So if you realize, oh, we have this debug mode still on, you don't need to do a redeploy that takes forever. You do config set debug false, and within 2 seconds, your application is back online with the new settings because it doesn't have to build code again. And this build code image you then use to run processes, right? So for a Python app, this usually means if you have some more sort of worker and then a built-in web server, Unicorn. And the same for Node. Node has a built-in web server. Ruby has a built-in web server. So for them, it's really easy because they can do setup work and then they bind to the port. Even Java, right? Usually a built-in Jetty or a Tomcat. And it can do its setup work. It can create some caches, warm-up caches even, and stuff like this. For PHP, it's a bit more difficult. A worker clearly that listens on a worker queue or a database and transforms images, that's simple. But for the web server part, it's kind of difficult because you can't do HTTPD something or Nginx because you also need to start FPM and stuff. I wrote a wrapper script that doesn't work in most environments, but you can still try it if you want. So we inject that, but there's different means. The future for PHP is hopefully going to be that now that PHP 7 doesn't crash the engine with a fatal error on a parse error because you include code, maybe we can actually start writing web servers implemented in PHP. It's probably still going to collapse when you exceed the memory limit. But PHP is getting closer to a situation where code runs that starts listening on a port and then runs Symfony in a constant loop, right, for every request. So once you have these processes defined, you achieve concurrency by scaling them horizontally, like the Romans did with the aqueduct bridges, right? So for instance, you have a service where people can upload images. Now, clearly, the uploads should not go to the server's file system because you're behind a load balancer, you have 100 instances, and what's ending up on disk 70, right? For the next request, you want to look at the image, you end up on disk 35. You all know this from PHP sessions. That's the reason why you probably upload straight to S3 these days with JavaScript. And then in the background, you enqueue a job on an AMQP service or something like this, or even just in a database to say, there's a new upload on S3. I please want you to create thumbnails for this, right? So you say, well, depending on the load of my system, these background workers actually shouldn't change, right? So you scale them to a fixed amount. Because you say, even if I have a lot of users on the page and they do a lot of uploading, then the uploads are going to take 20 seconds instead of 3 seconds to complete on a peak night, but I don't care about this. What I care about is that the front end isn't offline, right? So you should never do stuff like image processing synchronously in the upload process, because not only is it slow for the user, it also means you're tying up a PHP FPM process, right? So instead, upload it with JavaScript from the browser to S3 and do the conversion in the background. That's what this worker does, right? And then the web stuff, you can scale up independently. So the web interface is still zippy and fast, and you actually see there's 2 workers running, and now you have 4 web instances running, right? And then later, when you're no longer on the evening news or featured on Reddit or whatever, or Hacker News, you can scale down again the web interface, while the image workers always remain the same. So that's really important. And it would work the same with Docker, right? In Docker, you would have 2 containers. You have one container that runs your web stuff. You have one container or multiple copies of each that does the image processing. And they connect to an external database or worker queue container to fetch the tasks they want to be run or should be running, right? And you can then say, well, my worker queue system is a complicated Kafka thing, so you can scale that up, right? Individual parts, no tight coupling, no assumption that on localhost there is the Elasticsearch, because that only works for so long. Disposability means you sick term something, and it should actually shut down. Dev prod parity is important. I, on a regular basis, deal with, but it works on my computer, support tickets. And customers are understandably upset that they're unable to ship their physical computer to the cloud. So I work with them to figure out why, and there's many reasons. Logging, I'm not going to explain logging separately. You log to standard error, right? And then some external service, in the case of Docker, that's just the Docker run daemon, collects the logs on standard error into a log for the container. And then you can, through some other means, aggregate the logs of all your Docker containers centrally. On Heroku, you type Heroku logs, and if you have 100 servers running, you see the logs from all 100 servers centrally. There is no /debug.log that you then need to tail or something like this, because you can't SSH into an instance on many cloud platform as a service providers, right? And even if you could, how do you know which of the 100 instances to SSH into? So let the logs come to you. And admin processes are just like a worker or just like a web process. They just not run forever. They just run very briefly. So dev prod parity, keep dev staging and everything as similar as possible. So SQLite is not the same as MySQL if you run that locally, right? You're going to be running into certain logging situations that don't happen on your local box, but they happen in the cloud or on your production environments, even staging environments. Apache has different rewrite rules than Nginx, and you will get that rewrite loop on Apache that you don't get on Nginx. File-based sessions is a classic. So I sometimes get these tickets like, hey, I installed WordPress, and then I scaled to 2 instances, and now I get logged out all the time. Yeah, because you need an external logging session storage, right? And there is another big difference between PHP's file-based sessions and a memcached or database session that you wrote yourself. Because PHP holds a session start, blocks on session start, until all other processes, which can be only one at a time, that has the session start log open, has finished. So you never have race conditions with a shopping cart locally if you store your sessions on the file system. But you will all of a sudden get race conditions if people click too fast and stuff is happening too slowly in production if you store your sessions in database. So do that in development locally as well, so you catch these errors early. You can always apt-get or brew install whatever libraries and systems and things you need in Nginx or whatever, right? Or you use Docker or Vagrant, but do that. And finally, admin processes. You need to do a database migration, right? So if you install Drupal or WordPress, the Drupal and WordPress installers assume that you still, in this year 2015, you upload stuff to an FTP server, which is one computer. Magento does the same thing. You call /install PHP, install PHP writes a config to disk, and sets up a database. On Docker or on a platform as a service, that doesn't work, because even if you push up the code, the config PHP the installer runs is only on that one of 100 frontend nodes. And it'll never make its way back into your code, because the next time you deploy, that change is gone, right? So you need to build the config locally, make it part of your code, make it sure it reads from environment variables. Push that up. And then after the first time you deployed it, you run the initial database migration that fills up the database with dummy data. This seems trivial, and you probably think, oh yeah, that makes total sense as I tell it to you. But the new Magento 2 installer still doesn't do that. In the Magento 2 installer, you have no way of installing the system without creating a database, because somebody still has a sysadmin who does everything for them and later pulls out the config and hands it back to them so they can version it independently. But think about these things, right? There shouldn't be any config generation at runtime. So when you're ready to do your migration, use Docker migrations maybe, right? You deployed your code. Your code now runs on the web server maybe. It's crashing because it doesn't have a database, fine. Or you scale it down to 0. So you have the code, you have the configuration because you added a database, so there's a database URL. Now, the migrations are also part of your code base. So all you need to do is quickly on the production infrastructure, run a doctrine migrate, and it'll have the code, it'll have the config, it does the migration and fills up the database initially, right? It's really, really simple. Oops. Yeah, I can't see animations here, so it just disappears or not. Yeah, so that's how you do it, right? You do a run, you can do a Heroku run bash. you can do a Docker run something something. So you do Docker run something migrate, and it runs the migration in a Docker container that's spun up just for that one command. And that Docker container, through Docker networking, talks to the MySQL Docker container that's somewhere else, right? And after that, the Docker container is gone again after it ran the commands. That's the future of the internet. So try Docker, try Heroku, or whatever else. It's cool stuff. And once you start designing for it, you'll realize that your application structures become a lot simpler because they make a lot fewer assumptions about things. They become a lot easier to maintain, a lot easier to deploy, right? If you build a thing that works well on Docker or well on Heroku, it means it's super easy to deploy anywhere, even on your traditional infrastructure, because it's so much less tightly coupled to your crazy chef or puppet recipes that only your sysadmin knows how to maintain, and then he quits, and then everything's on fire, right? Anyway, thank you for listening. For those interested, I'll do a 5-minute Heroku Lightning Talk demo later, and if you stop by our booth, you can win an electric skateboard that we're going to be raffling off tomorrow during the closing session. Thank you.